Hey everyone, today I'm going to show you something that fundamentally changes how to think about secrets synchronization in Kubernetes. In today's demo, we are going to take external secrets operator, SO, and make it truly secure by eliminating its need to store secrets in Kubernetes entirely. So let's dive in, shall we? So let's start. So while external secrets operator simplifies secret synchronization from Vault to AWS Secrets Manager or Azure Key Vault and other similar secrets providers, this convenience comes with a subtle but significant security trade-off that's often underestimated. So to dive into that, let's look into how external secrets operator default flow works. So here is how it works by default. External secrets operator retrieves secrets from a upstream store. It can be HashiCorp Vault, it can be Azure Key Vault, or any kind of key store that the SO supports. And after fetching those secrets, it creates a Kubernetes secret object in the cluster that it manages. And then your workloads, your pods, your applications mount those secrets and consume them as Kubernetes secret mounts or environment variables, however they see it fit. So at first glance, this seems straightforward, but there are important security implications that is worth examining in here. So for starters, anyone with read access to secrets can decode Kubernetes secrets. There is nothing secret about K8s secrets, so to speak. So managing granular RBAC access around Kubernetes secrets is limited because it is namespace scoped. You cannot scope a secret by its value or by its key or by its path. So you cannot limit exposure, and auditing becomes a hassle as well. It's challenging. So in this demo, we'll explore how we are going to keep our secrets truly secret while still using external secrets operator, but without storing any K8s secrets in the cluster, thereby significantly improving our security posture. But what's the big deal? Why does this matter? So this design choice matters because while using Kubernetes secrets, we don't have encryption at rest by default. Secrets are stored in plain text in etcd. There are ways to encrypt etcd, and I'll delve into that as well. But let's keep that aside. The other important issue about Kubernetes secrets is the RBAC exposure. It's not granular, it's broad. So when you do a kubectl get secrets, it can reveal all of the secrets within a namespace. And also we lack audit and visibility. There is no native record of who accessed which secret or when. Secrets can persist beyond their usage, and those secrets remain in the cluster long after they might not be necessary. They might not be intended to be used ever. So that results in stale secrets, which can be another attack vector that malicious actors can leverage. So one thing that one might often think is, why not just enable etcd encryption? It's what everybody recommends, right? And it's a common recommendation, to be fair, and it mitigates one of these shortcomings that I have alluded to. And it's useful, but it's not so sufficient. Why? Because etcd encryption relies on keys that the API server must be able to access. So in practice, that means that the key must reside somewhere reachable by the API server. So if an attacker gains control plane access, then they can read the key and decrypt the stored data. So storing the key in an external KMS, you might think might a little bit make things harder. But from a attack vector perspective or from a trust boundary perspective, it doesn't really change the fundamental risk at hand, because the API server will still need permission to call that KMS. So if the control plane is compromised, so will the API server. And if the API server has IAM access to KMS, or the API server's IAM role is compromised, then an attacker can still decrypt every single one of the secrets in the cluster. So again, game over. So even when etcd is encrypted, so if an attacker compromises the secret, like I said, then they can get the decryption key. And like if an attacker compromises the KMS because the API server has access to that KMS, then we get the decryption key and we can decrypt all the secrets from etcd. So in short, when we keep the sensitive data in Kubernetes secrets, the cluster becomes our trust boundary. And if the cluster is compromised, the keys and therefore all the Kubernetes secrets are also compromised. So etcd encryption protects you from certain things. Like one of those is like stolen disk, which is really hard to steal a disk from a data center because it has physical protection at hand. But let's leave that aside. It prevents you from direct access without Kubernetes API. And like I said, it stores, it secures the etcd from physical media theft. But what it doesn't do is it does not protect you from things like privilege escalations or node and API server compromises, and things like container escapes, or like there's a 0 day in somewhere in the node, and like that node is compromised, then essentially those secrets are gone. So in contrast, when we compare the encryption mechanism of Vault or OpenBow, we can see a like drastic difference. But the fair thing is here, the encryption key lives inside the very system that we are meaning to protect. So this is like, I don't know, this is like hiding your house key under your doormat. In the setup, the protection mechanism and the asset that it protects share the same failure domain, which is not quite secure, to be honest. So let's compare this with how Vault or OpenBow does secret management. So Vault has encryption at rest and encryption in transit. So there is a layered protection across storage and network boundaries. And it has its own authentication mechanism, which is decoupled from the cluster identity control plane. So if you have a separate vault, then its protection, its trust boundary is different from your cluster. Vault has really fine-grained policy-based RBAC. So policies are in Vault defined per secret path rather than per namespace, which is much more granular. And with Vault, we have comprehensive audit logging. Every read, every write access attempt is logged with enormous detail. And there are also things like dynamic secrets, and we have automatic secret rotation, which makes obsolete secrets go away real soon. And Vault, like I said, is external to the cluster, or can be made external to the cluster. So when deployed separately, a cluster compromise does not imply a Vault compromise, which is really useful. And each access to Vault or OpenBow is traceable. You can see here a sample audit log entry from Hashi Vault. So with this log entry, we see who accessed the secret, the service account identity, what secret was accessed, the exact path that the secret was accessed, when the action occurred, from where, from which source we have accessed the secret, and under which policy is guiding this, or which policy is authorizing this context. So this level of visibility, or this level of granularity, is, to be fair, what Kubernetes secrets fundamentally lack. So in this demo, I'm going to show a multi-vault federated secret handoff pattern, which introduces a defense in depth across several trust boundaries, which will make things really, really secure. But before that, let's review the traditional model of SO once again. So here in this model, even when we consider SCD encryption is enabled, we have a single trust boundary. It's this cluster here. And everything is revealed when that trust boundary is breached. And in comparison, here is the vault-to-vault federation approach that I'm proposing, which compartmentalizes the risk into several trust boundaries. So we have here 3 separate trust boundaries, and you need to breach all of them to gain access to the entire kingdom. So notice what happens when the Kubernetes cluster is compromised in each model. So let's go backwards again. With the Kubernetes secrets only solution, if the cluster is compromised, then the attacker obtains encryption key and decrypts all of the secrets. So the blast radius is 100% of all of the secrets ever, which is not good. In contrast, when we do a vault-to-vault SO federation, the cluster compromise means the attacker still will need a separate vault credential. And even with downstream vault access, which is still harder because we have MTLS in between and we have short-lived tokens. So if you get a token, by the time you are trying to exploit that token, it will be expired already. But still, even if you access the downstream vault somehow, the blast radius is limited by the policy that manages that token. So we have contained the blast radius to a really smaller scope, essentially. So let's show a more detailed comparison chart between the two approaches. I'm not going to read all of these, but this chart kind of sort of summarizes how a vault-to-vault federation is a much secure, much trustworthy way of federating and synchronizing secrets, especially if those secrets belong to like a dear customer that they manage in their upstream on-premises on-premises secret store, like a OpenBAU or HashiVault. So keeping secrets outside Kubernetes means an attacker must compromise multiple independent systems to gain access to only a subset of secrets, and if that happens, if they are really lucky. So, okay, that's enough intro. Let's get our hands dirty, shall we? I'll show you here how to make external secrets operator synchronize secrets directly between two secret stores without requiring any intermediate Kubernetes secrets. So as a side note, this is not a this hasn't been implemented in external secrets operator. So I am forking and changing the source code of SO, but I am also doing this with minimal code change, and I'm trying to follow the patterns and practices in the external secrets operators code base, so that maybe later down the line we can merge it as a feature, depending on how things pan out. But let's first, before that, let's first dive into the actual implementation. For this, I will switch to my development server. Let me first find where it is. It's not here. Yeah, it should be here. I'll just clear this one first. Enter. Just give me a second. What? Okay. My enter key is a little stuck. The keyboard, I haven't been using it for a while, so I think it gets rusted. But I'll try to wing with it. So I want to start with a blank slate. So I'll just check my git status -s. I think I have some changes here, so I'll just stash all of my changes. And some of those changes are all generated code. So the actual code changes like around, I don't know, 70 lines of code, not much, based on the feature that we are going to implement at least. So, but still, let's begin. I'll clear this one, and then we are going to like do a minikube delete. I'm using minikube as a development cluster because it's easy to set up and tear down, and it is self-isolated. So it's useful in these kinds of demo instances, essentially. And then I'm going to do a minikube start. I don't know. I have lots of CPUs, but I'll just assign 4 CPUs and memory. Let's see. 8 gigs is enough, I guess. 8192. Enter. Enter. Come on. Enter. All right. So it will ask for my password because this is a secure Fedora. So it sometimes gets annoying. I need to enter my password. But I prefer annoyance than, less security. Let's authenticate with this one. This will take a while to initialize the cluster, but it's relatively fast. In the meantime, I'll check my notes and see if I'm missing anything. And I also sip some coffee because it has been a long day. We have been moving houses. So I'm tired, but I want to be done with this demo, hopefully with a successful outcome. Let's see. So next up, we are going to add OpenBow as a Helm repository. I'm using OpenBow, but you can use HashiCorp Vault. They are API-wise mostly identical, and either is good enough for this demonstration purpose. So I'll edit. It's already in my Helm cache, so it didn't. It says I already have it. You don't need to edit. So I just clear and go ahead. So next, I'm going to install 2 separate OpenBow instances. One of them will be our upstream OpenBow Vault, and you can think of this upstream instance as your customer's managed vault that lives on their premises or on their cloud. Typically, you won't want to change it. You don't typically have direct access to it, but the customer would likely want their secrets to be mirrored into your cluster, which is what we'll do here. But for this, let's create our upstream OpenBow instance first. This is the upstream one. The downstream one will be similar. And I am enabling the development mode. It is really not secure, but for the purpose of this demo, it's good enough. I just didn't want to do too much configuration because the purpose of this demo is not about how to best configure Vault. It's more about how we can modify external secrets operator so that it can enable vault-to-vault synchronization without creating intermediary secrets. So let's install our downstream Vault as well. Then let me clear this one. Oh, just give me a second. Clear. kubectl get, what do we get? Let's see, we get pods, which are OpenBow pods. Do I need to specify a namespace? I don't think so, because by default, it goes to the default namespace. So yeah, we have 2 OpenBow instances. One of them is downstream, the other is upstream. Upstream is our supposedly customer vault, and downstream is the OpenBow that will either reside in our cluster or tangent to our cluster in a separate trust boundary, which will make it extra secure. So that's that one. What else? So we need to change a bunch of things in the code to make this work. So for this, I'm going to open up my editor, colon load file system changes. So I'll start with data types first. So I honestly don't remember which type I changed, because the same type is defined in both V1 and also V1 Alpha 1. So what I'm going to do is I'm going to both, change the data definition in V1 and also V1 Alpha 1. And also I'm trying to explain why and what I'm doing there. So in external secrets V1, we have this external secrets types definition. And there we have, let me find what we have. Secret store, external secret types. External secret deletion policy. There should be a I'm trying to remember where it is. It's around line 480s. This is a virtual machine, and my Vim bindings are not working, so I just have to go by memory. So if memory doesn't serve me well, I'll need to scroll around, which would be fine, I guess. It shouldn't take too much time. So it should be around 460s or something. 460 data from external secret, data from ref. Yeah, here. So this is a external secret spec, which defines an external secret. So this is the data model representation of a secret to be serialized into a Kubernetes secret. So what we are going to do here is, let me move a little bit downwards. So I'm going to define a push target here. The push target would mean that we are going to, instead of pushing this secret to a Kubernetes secret, we are going to push this to a separate secret store target. And this will be optional, which means if you don't define it, the external secrets spec will behave as it did before. And I'll add other guardrails around this as well. And if we define this, and if the definition reconciles to a secret store that we know of, then it will push the secret into that secret store instead of creating the Kubernetes secret. So, but for this, we need to also define the push target spec. To save some typing, I'll again copy and paste the type definition, because it's essentially, it will turn into some API YAML models and some auto-generated code. And the more important part is the secret store ref and remote key. So one thing that's worth mentioning is here, we are not reinventing anything. We are using as much SO primitives and SO constructs as possible. So instead of defining, hey, I'm going to push stuff to HashiCorp Vault, I am saying I'm going to push, my push target is a secret store, which gives us the ability to declaratively defined targets. So if there is a new secret store that external secret operators start supporting, then we don't need to do any code changes. We can just point to that secret store, and the wiring behind the scenes will be done by external secret operator itself. So this is that one. We want to push stuff to secret store, but how do we want to push it? So at a really high level, a secret store is a secure in-memory key value store, hash table, to be really simplistic. So we are pushing a key and a value to a store. So this is our key, the remote key, and this secret is essentially our value. This is all there is to it for to define like type definitions. But like I said, I'm going to do this to V1 Alpha 1 as well, because I am not sure which one of those secrets I had to change essentially. So let's V1, not V1 Alpha 1, sorry, V1 Beta 1 maybe. V1 Beta 1. Let's check this one. External secret types. V1 Beta 1. In that one, I'll also again check my notes because I don't quite remember around where it was. It's around here, like it's right at my cursor. So I'll just select this part and paste the thing that I copied, and I'm assuming I copied this. Oops, my bad. I need to copy this, copy, and paste it here. And lucky me, there wasn't any data type, the data signature changes. So like a simple copy and paste like worked in both V1 Beta 1 and V1 implementations. That's that one. So we are done with the type definitions, but just defining these types isn't enough. Somebody has to use that type, and that somebody is the actual controller, which the bulk of the business logic is implemented. So let's also dive into the controller. But before going that, I want to collapse these so that I have some leeway to see, the folder structure. So this is the external secrets controller. That's where the majority of the work is done, and the actual work is done. Not actual work, but the reconcile loop, the control loop happens under this reconcile function. This is typical operator pattern essentially, and in that reconcile function. Let me see where we are going to modify. Let's see. We should be modifying something around line 400. Again, I'm going through my notes and my memory because, like I said, my ID is like... that's the problem of live demos, I guess. If something is going to go wrong, it goes wrong and you end up debugging. And later down the line, you do a post-production and cut stuff out, essentially. That's why all of the tutorials that you see around seem so well polished, but nobody sees the behind the scenes. The behind the scenes, to me, is the actual fun part, because there, like, you figure out how you debug stuff, how somebody debugs stuff, and you see into that person's like mental machinery. I would really love somebody suffering rather than somebody like being awesome, essentially. But maybe that's just me. Let's see. Like I said, 400 somewhere down here. We have a mutation function. And yeah, so we have a switch yard down here. So if we have a data map and that data map is a secret, it does a bunch of stuff here. Let me double check. External secret spec target policy. There should be a switch for external secrets target policy. Am I looking at the right thing? Let me search for this mutation function. It's here. Yeah, perfect. So this is the switch chart. So based on what data that comes and what policy is defined, it does a bunch of actions. What's fun is this part. So there's a create policy none. It essentially says if you define a create policy none, then external secret store will not create any Kubernetes secret no matter what, which is useful for testing purposes. So if you are writing an integration test, then not creating secrets but just testing the behavior will make like cleaning things up easier, will make the tests run faster. But here we can use this to our advantage, which is really fun. But still, I just want to dig into the definition, declaration of this one to see like whether I'm doing the right thing. So when I go there, it says it does nothing as we expected, and it says future use with injector. So essentially, we are at the moment defining that future use by creating a kind of sort of injector. I don't know if I'm creating the right injection pattern, but I'm assuming I am more or less following a certain way of doing things. I am planning to discuss this with with SO team later down the line if I find a chance. But right now, I'll just go put my hacker's hat and like go on hacking. So let me go back to, how do I go back? So secrets controller, go back here. So what we'll do is, let's comment this out as well. So we'll add a control essentially. So if external secret, which is our don't autocomplete AI. I don't want you. External secret that spec that this thing that we just defined, push target, is defined, isn't nil. We are going to do stuff. Otherwise, we are going to preserve the existing behavior. So I'll just drag this down here. So this is how things used to be. I'll just remove these comments. So essentially, if we don't define this, we are preserving behavior parity. And this is a new feature. So we essentially what we do is we are not breaking backwards compatibility. Anything that we like, the thing that we define is a new attribute. So if nobody uses it, nothing happens. If somebody uses it, then like the behavior will change, obviously. So what we want to do here is I want to push the secret to the target store. So I'll just, instead of punching down a bunch of keys, I'll just paste the code here. Paste. So we'll say, hey, I'm like pushing to a target store instead of creating a Kubernetes secret. Just a good code logging sanitization, I guess, because this is a new behavior. We want to like inform, and also I'm following the pattern. So we did a info here, so better to do this info line here as well to mirror the behavior. But the thing is, we haven't defined this push target to store function yet. So for this, I'll go to the top of this struct, object, class, whatever you call it. And I am going to define a reconciliation push to target store function. So I'll just, this is like 50 lines of code, so I don't want to type it in for two things. It's like 11 p.m. almost, so I may be prone to making mistakes. And the point is not writing the code, but the actual point is like seeing and understanding the code. So instead of just punching things in, I'll explain things along the way. So what we do here is we are creating a secret store manager. And as its name implies, Secret Store Manager manages secret stores. So using this manager, we will get a reference to a secret store. This target client is a reference, a client that can talk to the secret store. And this target store ref is the secret store reference that we get from push target. So this target store ref is our Hashi vault or OpenBAO, which is cluster internal. And this target client is a client that knows how to talk to the store. So here we are creating a V1 secret Kubernetes object, but the trick here is this secret object is just for like bookkeeping purposes. It's a an object that remains in the data, and it goes through certain mutations. But in the end of the day, we don't reconcile it as a secret. We show it to the secret store in a way that the store expects. So that's how that's done. And that's done by passing the secret to the mutation function, similar to how the secret is passed to the mutation function in other handlers as well. Then we create a remote key reference, which is the path to push this secret to the store. And after that, it's just calling the target client's push secrets method with the secret that we created, the metadata that we created, and with the secret, which essentially pushes the secret to the OpenBAO instance. So we are not creating a Kubernetes secret to be specific again. We are just delegating or like synchronizing, funneling, however you call it, the secret to the internal OpenBAO. So from our perspective, our secrets are OpenBAO secrets. So that's that one. And that's all the code we need, I guess. So let me check my notes again. Yeah, I think I'm not missing anything. So let's go build this thing. For this, I'll go to my terminal again, and I'm in the external secrets folder. So since we created a bunch of data types, we need to generate manifests and generate source code so that our operator can know what it's dealing with. So for this, I'll do a make generate, and then do a make manifests. So it will create some YAML foo as well. And that's mostly the code generation part. So now we need to create a custom container image and push that image to our repository so that we can like reference it in our YAML files. So let's see. For this, I am going to do a make Docker build. Again, I'm going to copy and paste this. Paste. It's just one line, but I just don't want to make a mistake. And I don't think this image environment variable has any effect, but I'm just defining it just in case. So it will like build the image, and hopefully I didn't make any mistakes. So it will compile it, build it, bundle it, and push it to my internal Docker, local Docker instance. And then we are going to move this one to our Minikube Docker registry. It shouldn't take so long. Yeah, it didn't. So, okay, I'll do Docker images, grep for custom. Yeah, we have an external secret custom Docker image. So typically you would push this to a actual registry, but Minikube has this convenience function that you can just internally load images. So that's what I'll do. I'll do a Minikube image load external secrets custom, which should, yeah, it did it. So that's that one. So the next thing is we want to deploy a external secrets operator. So ls, I'm trying to find a proper folder that I can go into hack, I guess, but let me create a like scripts, because like I don't want to like meddle with things that I shouldn't. So let's vim, what do we say? Install SO custom or SO federated, because we are doing federation. So federated makes more sense than like custom to me, because I don't know, like naming things that are hard, and I don't like to be lazy. Well, I like to be lazy in certain instances, but naming is not one of those. So user bin env bash. I just paste stuff again, and then I might modify, because I might be pasting from an older backup copy that might require some modification. I'm not sure, but we'll see. Let's paste it. So let's double check. Helm install external secrets, system, image repository, external secrets, tag custom, image pool policy, never. This should do it. Let's save this, change mode. Then install SO federated. Let's wait for it. Okay. Kubectl get pod -n external secret system. Enter. Ah. Image pool policy, never. Didn't it find the image? Let's see what's happening. Copy. Kubectl describe for external secret -n external secret system. Container image. Oh, I did a typo, external secrets custom. So let's edit this one. External. Insert external secrets. Helm ls, upstream open bar, downstream. Okay. So the other Helm install hasn't succeeded, so I can execute this one again, hopefully. Enter. Okay. Uninstall external secrets. What's the release? External secrets, external secrets, external secrets. Well, I am lazy and tired. It has been a long day. I'll just ask Cloud AI to find the right uninstall command. I want to uninstall this. Okay. Oh, yeah. I had to provide a namespace. That's the problem. Okay. Let's do that one. Helm uninstall external secret system. Enter. It should hopefully wipe it out, I'm assuming. And now if we do install SO federated, it should have installed stuff. Let's see. Okay, it's reconciling. I'll wait for all of the images to be ready, and they are. So far so good. At the very least, our controller hasn't broken. Things are supposed to be working, but it doesn't necessarily mean that it will work as we have defined. So fingers crossed. So we have 2 Vault instances, but to be able to use them, shell into them, we need to create tokens. The good thing is these are development Vault instances, so I can just create secrets and bind them. So let's do this one. These secrets will be used by HashiCorp, not HashiCorp, sorry, the upstream OpenBOW and downstream internal cluster, internal OpenBOW as well. So while here, I want to add a segue here. Let me go back to my speaker deck if I can find it. Where is it? Did it? Let's go down. So we set our environment, and we have been so far the entire theme of this thing is to not create secrets, but here we have created secrets for the OpenBOW instances to use them. To be really clear, this is not for production use. So I am creating these token secrets purely for demo purposes. But again, let me be very clear. This is not how you would configure your vaults in production. And like I said, there's a bit of irony here. We just spent half an hour explaining why storing secrets in Kubernetes is bad for security. And now I'm storing vault credentials in K8s secrets. It shouldn't be reasonable. So because if an attacker gains cluster access and can read those secrets, then they'll get both upstream and downstream vault access. In other words, we haven't solved the problem. We have just moved the problem. So in production, you may use a bunch of things. One of them is SPIFFE Spire, the cryptographic workload identity with 0 manual configuration and automatic credential rotation. It's used pretty much everywhere. Microsoft Entra ID uses it, GCP uses it, Amazon, some identity control plane that I don't remember uses that as well. So that's a really solid choice. Another thing that you can use is Kubernetes Auth. Vault can authenticate with workloads through their service accounts, so you won't need any static tokens stored in the cluster, and the tokens by default will rotate every 15 minutes. Or you can use like Cloud IAM. You can rely on AWS IAM roles, GCP service accounts, or like Azure managed identities for authentication, for example. So my preference, as you might guess, is SPIFFE, since it offers like the strongest security posture in a zero trust cloud agnostic way. But that being said, your infrastructure is your infrastructure, and your operational model is like your operational model, and your risk tolerance is yours to decide. So those might lead you to choose a different approach. So pick whichever of the options is best fitting your environment, aside from using a static token, because it's really it's not secure. With that clarified, let's continue with our demo. I'll shift to my terminal again. Let's see. So I'm going to first act on behalf of the customer, and I'm going to populate the customer's vault. And for this, I want to create a script because I am feeling like the Murphy is like breathing on my neck. I might make a mistake. So instead of like pasting in the terminal, it's better to edit scripts. So I'll do a vim customer vault populate.sh, enter user bin env bash, escape, set paste, enter. But that paste, insert. Then let me paste this thing, and let's see. We've exec upstream open bow shell. This is the default vault address. This is the default token that we set up. We are putting a secret prod db creds, username prod user, password super secret password, to our upstream customer HashiVault. So change mode. Let's say start u plus x, all shell scripts, then customer vault populate. Whoop. Okay. Yeah. Yeah, I'm missing this one. Insert. That should hopefully do it. Yes, we have a secret in customers secret store. We have the secret path and secret metadata. I just copied this one for future preference purposes because just give me a second. You might know that I'm also leading a secret store solution, which is two secret store solutions actually, but one of them is taking more of my time at the moment, which is Spike. And Spike like walks and talks like Vault, but arguably more SPIFFE native and more focused. So I want to align how it reports stuff with how Hashi reports stuff. So that's why I copied this one. So we created the upstream secret, and now let's create some YAML files, because I don't know, where's the fun in platform engineering if you're not writing YAMLs? No? Yes? Okay, let's create I'll continue like playing around in this scripts folder, make their manifests. cd manifests clear. So I need to define two secret stores. One of them is upstream, the other is downstream. Vim upstream store. Let's say vault, upstream vault YAML. Set paste, because again, I don't want to make a mistake. So I'll just paste the things, because YAML is really prone to like white space errors and indentation. And I want to finish this before midnight. So mercy on me. External secret store upstream vault. Provider is this one. It's upstream open by default service cluster local. And we are using this upstream OpenBAO token reference. This will define one secret store, Vim downstream vault YAML. Again, set paste. Boop. I'll copy a YAML and paste it down here. If I can find where to paste. Escape. That's the downstream vault. Okay. These are the secret stores. Let's apply them first. Kubectl apply -f upstream YAML. Okay. Upstream apply -f downstream vault. So I have I have defined our secret stores, which now the external secrets operator can know and reason about them. Now we are going to define an external secret that will say, hey, I have a secret in this customer store. Can you please, if you don't mind, mirror it in our downwards local secret store without creating any Kubernetes secrets? So I'll say this, name it as Vim external secrets YAML, because right now my brain feels like Jello and I cannot find the proper name for it. Enter. Set paste. Enter. Let's see. So I'll copy the YAML declaration that I have and I'll paste, and I'll then double check just in case. So we have an external secret. We are referring the upstream vault to fetch that secret, and this creation policy none hints that, if you remember, we had a fork for the creation policy none. We modified the behavior there. So it says that, hey, we are not going to create any Kubernetes secrets, but hey, also we have a push target. So don't be lazy. Just, consume this push target and create a downwards vault secret instead. So, and that push target refers to our downstream vault with this cluster prod db creds remote key reference. So refresh interval is 1 minute. So I might need to wait a little while for this secret to reconcile. But my hope is once I converge this, I create this external secret, it will pick the secret from upstream vault, create it in the downstream vault without creating any Kubernetes secrets. So let's save this one. Kubectl apply -f external secret YAML. External secret inversion cannot be handled. External secret stick. Spec push target. Oh, okay. Let's see. External secret in version v1 cannot be handled as an external secret. Secret decoding error. Let's trim this one. Uh, Let me quit this. Cannot be handled as external secret. I'll copy this one. I'll check my notes again because I remember having faced this issue before. This might take a while. Because, yeah, silly me. I generated the code, I generated the manifests, but I haven't applied the CRDs yet. So to be sure again, I'll do a make generate, make manifests, and then do a make install, which will install the CRDs to the cluster, hopefully. But not here. Up. One more up. Make generate, make manifests, make install. Let's see. Undefined variable is no rule target install. Okay, because it should be CRDs install, I guess. My memory, if my memory serves me well, make CRDs install. Yay! We have our CRDs. So we have custom resource definitions. So if I go to scripts, manifests, and then if I try to, where is this one? Apply external secrets YAML again. I'm getting the same issue. Because I think I might have gotten a conflict somewhere. I'll just force update the deployed CRDs. Good. Deploy CRD. Nope, it doesn't have it. Let's see. Make CRDs install. Not here. CRDs install. Using API extensions, K8s v1 spec versions. I will just debug, and I'll probably like edit this part out because I'll be doing some debugging, and I'll at least summarize what happens in the end. I don't have the CRD. There's a conflict. Let's paste this one again. Okay, I force updated them, and it looks like, yeah, we now have push target in our CRDs. So hopefully this time it will work. I'll again go into scripts, manifests folder, and then kubectl apply, not this one, let's find this one, apply -f external secrets YAML. Yes, external secret is created. So we have created the external secret, but that doesn't necessarily mean we have synced it to the downstream vault. So let's double check that one as well. Just give me a second. So I'll go one level up. I will create another script when print downstream vault. And just name it this. Set paste. Insert. Again. Shebang user bin env bash, and I will do a kubectl exec on my downstream OpenBow instance while hoping to see the secret propagated. If it's not, I'll have some fun time debugging. If it is, then we have done something that hasn't been done before. Both of them are fun options. We'll see how it goes. Change mode. U plus X, U star sh. Then print downstream vault. And bingo. So we have propagated a secret from upstream customer mimicked vault into a in-cluster vault successfully. So one thing that I want to double check is how many secrets I have in this cluster, and whether this OpenBow still created a secret for my secret. If it is, then we have all of our efforts have been in vain. But if it hasn't, then like I said, we have done something that hasn't been done before, which is essentially innovation, I guess. Kubectl get secret -all. Let's see what we have. Downstream OpenBow token, that's fine. Helm related secrets, those are fine. Upstream token, that's also fine. Webhook, Helm Bootstrap token. So we don't have any secret that refers to our super secret password, which means we have successfully created a Kubernetes secret with external SO federation, essentially. So that's really useful, and I think there are many use cases that this opens a door to a better, secure way of managing secrets. Let me go back to my speaker deck. Let me see what else I have. Back. So this was vault authentication methods. So I want to like show you what we have done and also provide you one final comparison to drive this idea home. So with traditional SO, we were creating a in-cluster secret. So when the Kubernetes cluster was compromised, an attacker would gain access to the API server, and then they can either obtain the encryption key or decryption key through KMS access, and then decrypt every single one of the secrets, 100% of them from etcd, which is game over. So in our new model with federated SO, when there is a compromise in the Kubernetes cluster, well, there is no secret stored in the Kubernetes cluster, so attacker is, well, what's happening? And then they may attempt to access the downstream vault, but they have to get a separate vault authentication token. And if we are using SPIFFE, then the credentials are short-lived and guarded by SPIFFE MTLS anyway. And moreover, the secret access is restricted, hopefully, by vault policies. And all of the activity of the attacker is comprehensively audited. So even if successful, only a subset of the cluster or only a subset of the internal cluster local vault secrets will be exposed to the attacker. The upstream production vault will remain protected, and the blast radius is really contained. Like I said at the beginning of this talk, this isn't about encryption. It's about secure architecture. It's about forcing an attacker to compromise multiple independent systems tortuously, and each of the system will have its own authentication boundary. And then while doing those, the attacker will be audited at the every single step along the way, which is good security. And also it's convenient, like, because sometimes there is a delta between convenience versus security. Security can be tough. Security can make you wake up at 3 a.m. On a pager call, but this is the opposite of it. When you define it the right way, then you end up sleeping more. So I think this finalizes our demo. And as far as making external secrets operator directly store its secrets to a designated cluster internal vault instance instead of using a Kubernetes secret to back things up, that's all there is to it. So until next time, keep your secrets secret.